Okay, so now let's bring this idea of arc length into the world of surface area. Now, for surface area of a cylinder, it's really easy, right? The surface area would be 2 pi r h. If you remember this, you picture yourself just having a straight right circular cylinder here, even if it's not a very long, tall one, right? And we know that all we're really doing right here is treating this strip as though we're getting the surface area of that strip as if we unfolded it. And so what's the length around that strip? Well, it's the circumference times the height, right, which is our thickness of this cylinder right here, right? I mean, it's not a very big one, but it's a cylinder nonetheless. There it is. Okay, so there's our cylinder. Our circumference is 2 pi r, and we're just multiplying it by its height, h. All right, well, how are we going to rectify this with the fact that we're going to get some strips, and those strips may not be nice straight cylinders, right? One by one, if we were to look at, let's say, little strips of this particular curve going along right here, and then we were to revolve it, will we be able to say the same thing? Well, the way to picture this is that we can say a very similar thing. Only this time you imagine that we're going to have a trapezoidal strip rather than a rectangular strip like we would have for this cylinder, right? So what would we say? Well, in this case, right, our area, our length along this curve is what defines the outer edge as we rotate it around. And essentially, maybe the way it might help you to think about this is that instead of having a single radius, what we're going to do is we're going to say, well, there's some radius somewhere in between these two, such that if we were to maybe rewrite, shall we say, our cylinders, our trapezoidal cross section into a cylinder, right? That it would be, well, probably about the average height right here. So in other words, we'll picture a radius in each uh, integral there that's equal to our average r1 plus r2 over 2 radius, right? And so that Ri right here, we could say, well, then our surface area of that particular strip is going to be likewise uh, 2 pi. It's going to be likewise 2 pi times the average height, h. All right, so that radius, where are we finding it? Well, what we're doing is we're saying that within each one of our delta S, uh, we'll call the surface areas here, delta S, right? It's the surface area of this particular strip, and you see that we have many of them that would go throughout this curve. We're going to have 2 pi times the radius, and then the length of the curve times delta x right here, right? So each of these things right here, this is the length of that strip, its length, times the radius, that's pi times 2 pi. All right, so here's our formula. Surface area is equal to 2 pi times the integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. Let's try this out with an example. Let's say we've got a simple one. We've got the curve y equals the square root of x on the interval from 1 to 4, and we're going to rotate this about the x-axis, and we want to find out what its surface area is going to look like. So of course we know what our curve actually does here. We're going to take our y equals square root of x curve, and we're going to rotate that about the x-axis right here and create a surface area for the shape generated by revolving that around the x-axis. So what would that surface area be? All right. So our formula tells that the surface area is equal to 2 pi times the integral from a to b of the function f of x times the square root of 1 plus the derivative of f of x squared. So let's get the pieces together right here. We know that in our case, we're going to have a and b, equal to 1 and 4 respectively. We know that our function f of x will be our square root of x function. So I'll write this way, x to the 1/2. And that our derivative f prime of x will be 1 over 2 x to the 1/2. If we remember how to do that. So we're going to rewrite our surface area formula this way. We're going to take the value 2 pi times the integral from 1 to 4 of the square root of x times the square root of 1 plus 1 over 2 square root of x dx. All right, well, here's another problem that cries out for a bit of simplification. So let's go ahead and do that. Oops, before I forget, yep, we still have to square this guy, right? Okay, so let's simplify. Okay, so if I take this guy right here and I combine these quantities under the radical as a single fraction, let's see what's going to happen. I get 4x plus 1 in the numerator and 4x in the denominator, and when I take that square root, oh, look at what happens right here. Isn't that nice? We've got square root of x, and we've got square root of x out here, so those things go away. And of course, now we've got 1/2 in our integral, so now we're going to get an integral that, once we've rewritten it completely, is going to give us a surface area equal to pi times the integral from 1 to 4 of the square root of 4x plus 1 dx. All right, we recognize this as a simple substitution again. Let's replace u for 4x plus 1. So that du is equal to 4 dx. And making the replacements right here, we're going to get a surface area that will be an integral of pi over 4, because we're going to take 1/4 over in our du to get dx, u to the 1/2 du. And if we evaluate our endpoints for u at 1 to 4, u at 1 is going to be 4 plus 1, 5. U at 4 is going to be 4 times 4 plus 1, 17. And so we're going to get a surface area equal to pi over 4 times the quantity 2/3 of u to the 3/2 evaluated from 5 to 17. Now, I mean, I'll admit most people don't like numbers like 17 and 5. I happen to like them. They're nice prime numbers. Haven't gone around and hurt anybody with them yet. So rewriting our expression right here and simplifying, when I evaluate this, I'm going to get pi over 6 times the value 17 to the 3/2 minus 5 to the 3/2. And we can work out a decimal if we care to, or simplify this somehow, radicals. But I think we've done a pretty good job right here of finding the surface area of this curve.